Hello, everyone. Good morning, good afternoon, good evening, depending on that part of the world from where you are joining in. We hope that you are doing well, and we thank you from the bottom of our heart for being a part of our 3 year journey. So, this is our third anniversary month, and on this anniversary month, we are super glad to host Luca. He's a Kaggle grandmaster and a Google developer expert in machine learning and the author of 10 plus books, I think now. And I think that we will try to utilize this session of ours to learn more from him, from his experience. But throughout this session, we would be majorly focusing on today's topic, that's deep learning for credit rating. And I think we can get a lot of learnings on this topic from Luca because he has been working into this domain and has a little bit of grip on this topic. Over to you, Luca. Thanks for your support to join us on our third anniversary month.
Thank you very much, Jan, for the invitation. I'm grateful to be here with all you. And yes, this is a Kaggle meeting, so basically I should be talking about Kaggle, right? And okay, I also have a book now just out. It's about Kaggle. It's called the Kaggle book. So maybe you are expecting something like that. But it has been a few months. I really couldn't do any Kaggle competition at all because of too much pressure from work and the launch of the book and a lot of issues. So when Ian invited me, I thought a little bit and I decided to present a work that we made as a team in my company. Why? Because this work has many inspiration from Kaggle, and it is the good grounds to show, first of all, a work on tabular data using neural networks, which is something which can be topic of wide discussions in the Kaggle community. And then I will have the occasion to point out how Kaggle has helped me and the team I work in finding ideas for a real world problem. Because in the end, what I want to communicate to you about Kaggle is that it's a great place for competition, it's a great place for showing off your abilities, but also a great place where you can build the skills that will be useful in your career. So if you would like, I can start and start sharing my presentation. And of course, if you have any questions, devote about a quarter of an hour to any, questions, idea, doubt you may have. Also, besides the presentation I'm going to give you now, so you can ask me anything you want about my Kaggle experience, writing, my Kaggle experience, writing books, and so on. So let's start with this presentation. This presentation is Deep Learning for Credit Rating, and is a project that we have developed in the company I work for. The company is a bank, and it's called Illimity. It sits in Italy and is a bank specialized on one side in non-performing loans, so loans that actually have some problem, and then as a digital bank, it provides service and financing for both the customers as you me are, and for companies. But let's start. I will just make it quite brief, my presentation. It won't take so long, so I estimate about 35 minutes. So we have a lot of time for all your questions. And first I will give you some context, because I do not expect you are coming from finance, and so you know all the details of what I'm going to present as an application in the banking sector. Then I will talk a little bit about the data and the processing workflow, and I will spend some time talking about the deep neural network model we used. I will explicit the results, of course, why we are so proud of the work we have done, and I will just point out how we kept on building on those initial results, getting more and more insights about how to leverage neural networks for tabular problems as the one I'm going to present to you. So before I proceed, I just remind you that if by chance you have any particular, doubt or curiosity about more in detail the model we used, everything is public and has been written in this paper called An Artificial Intelligence Approach to Shadow Rating, where you can find everything is in an archive, and you can download it for free. Basically, as you can see, is made by all the team. This is the risk analytic teams led by Giacomo Lepera, and with the supervision of our risk manager, chief risk manager, Claudio Nordio. And this project has been one of the first ones I have been, taking in as soon as I started this new job in this bank after a long experience in insurance. So you can imagine I was quite excited. But let's start with some background, because probably if you're not from the banking field, you may wonder what's about this shadow rating, what does it mean? So let's first start from a very simple idea that you have to evaluate the risk. And in the case of a bank I work for, the risk for companies is very important. The risk can be expressed in various ways, but for the moment, let's just think that is the risk that a company will default. So the company won't be able to provide you, for example, the money you lend them. And if you go around in the financial world, you will find companies such as Standard & Poor's, Moody's, and Fitch that they provide credit risk indicators in the form of alphabetical letters. How do they work? They provide a set of letters that can be intended as clusters, and each cluster, which is composed of different companies, has exactly a very precise likelihood of being in default after a certain leg of time. In the case of most of these ratings is about 3 years. So you look in the future, and you have a certain expectation that in 3 years, a certain percentage of that companies inside that class defined by that letter will default, won't be able to give you back anymore the money you lend them. Obviously, the higher better scores, which is the triple A in this case, have almost a very small, slim chance of being default. But on the other side, you have a certain expectation quite high that some of the companies in that set will probably default. And this is very useful, because if you are not just betting, so you're not lending your money to just one single company, but to many, using these kind of ratings can help you to assess how risky is actually your business in lending money. And obviously, you can buy this kind of ratings, you can build them in your own company. Your own company could be a bank or a financial institution. Of course, you can do that if you have a lot of data. And the company actually I'm working for, this bank, is a new bank, is a new paradigm bank, is a startup. It has a little bit more than 3 years of life, and actually doesn't have so much data to leverage. So at the beginning, it was quite important to think of a way of leveraging existing ways to rate risk for companies, especially in the light of a kind of call it portfolio, of a kind of set of companies we were going to hold to be accounted for. And there's a way for doing that, actually. It's called shadow rating. And here I quote this process from a text in our field. It is the Basel II risk parameters from Springer. And there's a professor, Erland Meyer, that explains that shadow rating approach is kind of model typically employed when default data are rare. So you don't have the data to build such a model, or it's a little bit difficult to get the data for the kind of companies that you need for. But it's quite easy to get external ratings from the major rating agencies, especially free ones. And you can build your own model. So it's a way to leverage outside data. Usually, traditionally, this kind of work is based on your portfolio of companies, on the ideas of business you are going to take in to lend the money to, or to get the debt, the non-performing loans in this case. You, based on your portfolio, you just define risk factors. So you get the information about the competitive environment, the economy, and all the information about the companies. It is very important to notice that the three major rating companies do have their own methodology when they assign the ratings to the companies they evaluate. And they declare that their method is both quantitative and qualitative. It means that they leverage both quantitative data, there could be balance sheets and other information about the company, or quantitative, but also qualitative ones, which could mean, for example, expert evaluation. And particularly, they don't explain how exactly they do such evaluation. So we can imagine, and Erlenmeyer reports to us, that actually they are using some kind of non-linear model. And they are also, typically evaluating both, for example, the probability of default, which is our sector called PD, so the probability that after a certain time the company won't be in business anymore, but also in the case especially of Moody's, they can also assess the importance of the loss that can you expect from them, because most often the rated companies are quite large and they have various obligations toward different bodies. So they don't have just one, we call it exposition, they have multiple ones. And it's also important to get an idea, if they will default, what will be the amount of loss that they can cause by their defaults. So based on your risk portfolio, you just gather all your features. And don't forget that it's also very important to get information about the economic situation, so the macroeconomic factors. And you use a model. Traditionally is a linear model, a linear regression model, could be on the log of the probability of default, or you can use a GLM. Typically is an order probit model, kind of a little bit sophisticated GLM for guessing about count data and in order way. And then, of course, you have to get your target. You pay these rating companies, they provide to you the target they have, so their classification, the rating classification. And by using the model, you just relate the information you have on the companies with the results, with the output that is provided from the rating companies. So you can shadow, just mimic their own way of predicting the ratings in a certain way, better or well. Actually, this is exactly what we did in a certain way, but we wanted to do something innovative. So we didn't want to use the classical models, linear ones, and try something more challenging. Here I'm expressing to you that we are going to use a deep neural network, but we actually try everything. So we also have the traditional models as a comparison, and we also have a gradient boosting. But we found out that using the deep neural networks brought a certain advantage, which was quite huge against the traditional models and a little bit slimmer against the IGBM, for example, approach, but still better than using gradient boosting. So this is also the reason why I present this work with a certain attention to what we did at the model level, because it will explicit to you exactly where neural networks can be better or can offer a different perspective, a different way of modeling for certain problems. So getting back at the data, just a very quick overview. We use balance sheet indexes and ratios. So they are indicators taken from the balance sheet that each of these companies produced, and we combine them into KPIs, so special indicators that they tend to give important information about the company. What did we look for? We looked, for example, about the profitability, the efficiency of a company. So inside the efficiency, there's the cost in respect of the output that they produce. And then we looked at of course, the cash, so the ability to be liquid, and especially also to ability to be solvent. So if they don't have the cash, if they can immediately provide in some way, maybe getting some financing or selling some other assets. So we focused on these kind of characteristics. And as far as, of course, the macroeconomic factors, since basically we work with companies in the Eurozone, and from different countries, we gather the macroeconomics indicators for each of its countries together with all the Eurozone indicators, because they can provide information about the tendency of economics dynamics inside that area and the tendency of economics dynamics inside the specific sub portions of that European area. And then we use the rating classes. We decided for Moody's because, as I mentioned before, if you remember, it does not tell you the likelihood of a default, but also it provides you some information about the entity of a loss that you can get from a default. Then we combine everything in a DNN, and we got, of course, predictions, but also we work with explainability in the sense that we produce for each prediction the shape results telling the user of the output exactly what feature, what characteristics combined gave that certain output. Because after all, you can imagine banking sector is very regulated, and there's a certain kind of experience that is really efficient in comparing and explaining situation about, for example, a default. So providing a complex model is fine, especially if it is very performing, but it's very important to be able to explain and to give a reasonable reason why that model provided that kind of information. So I mentioned to you about the data is about companies in the EU area, but I will give you more details now, which are useful just to understand, especially the scarcity of the data we work with, which is very important for the kind of work we have done and for your evaluation about any kind of application of tabular data to neural networks. So we use a sample about 2,500 rows, examples, let's call them examples. They are not different companies, because in the end, the unique companies were about 500. So you can imagine they were actually the same companies over a period of time. So they were not IID. So basically, you had companies with data probably continuous in time from a range of years, ranging from 1996 to 2018. And sometimes we had gaps and so on. But it's very important, this aspect, because as in many Kaggle competitions, taught to us, when you have non-IID, so not completely independent examples, probably some, targets you are going to analyze are very correlated to other ones. And what happens when you apply a model and, for example, you have a company, let's call it company A, and you have a few years, in training and a few years in, for example, your validation set. It happens that actually the model can learn something from the data you provide, which is not actually generalizable. Since some information are correlated already inside the training, the model can catch that maybe it's easier not to guess your target, but to guess that you are dealing with company A in order to predict better at its best what is dealing with. So you can have kind of inflated output in the sense that you can get the idea that your model is really performing very well. Maybe you won't guess all the companies, of course, you have provided to, you have provided your model with, but it's enough that you can guess a few ones to spoil your results and maybe have better feedback from a certain kind of model than from another one, maybe with less variance and more bias, which may be more suitable. So it's very important, and we learn this from Kaggle competition, to cross-validate correctly. And in this case, it's essential to use group k-fold validation. So you have to segregate companies or in train or in validation. They have to be separate, completely separate. Of course, you can, and you can apply certification, because in this case we have different countries, so we wanted to have countries well represented both in training and in validation, but it's very important that the same company or is in train or is in validation, because otherwise you can have inflated results. And okay, basically it's important for you to know that there were companies, not institutions. So you don't have banks, you don't have kind of public bodies, you have companies from many different sectors, and we use balance sheets, macroeconomic indicators, and all these data basically apart a few very important features were quantitative or kind of low categorical features. We could be very easily one-hot encoded. So basically, you had almost all quantitative information. And in case we missed something, we found more useful for our program to use the median, but it really depends on your problem. Sometimes the mean can be better. The only problem was that with some categoricals, we really have a very high space of different levels. And I mentioned to you the sectors. The sectors are very important. And in a few slides, we will see that we applied a solution for high categorical features using the embedding, which is one of the reasons why sometimes your neural networks perform much better than gradient boosting. Just a note, we processes all the numeric variables using quantile transformation. It worked very well in this problem. Sometimes I myself recommend to try it. What is quantile transformation? Basically, it's something that you can find in the scikit-learn package, and it just takes your categorical variable, your quantitative variable. It builds the cumulative distribution, and then based on that cumulative distribution, it just redistributes it in order to represent using quantiles, using a distribution of your preference. Usually the normal distribution is the one of choice when you are working with neural networks. Okay, here I have the example about quantile transformation, and you see everything is arriving from the scikit-learn preprocessing module, and you import the quantile transformer. And in this case, you have very skewed distribution, which is, of course, something that can be dealt by a neural network, but it's better, of course, to transform it in a more resembling the normal distribution, because also outlying cases will, be more evident for the neural network. This is obviously a nonlinear transformation, but of course, you are using a neural network, so even if you are losing some of your linear correlation that you initially have from your features, it will be in some way, if it is necessary, rebuilt inside the network itself. The most important aspect is that it helps you to normalize all the features, to make all the features the same for your neural network, and that they have a quite balanced and symmetric distribution, which makes your neural network work better and converge faster. We also work a little bit on the target, and this is just very easy approach. Of course, from Kaggle competitions, a lot of ways when you have unbalanced data sets. In our case, we were driven mostly by the kind of problem we were dealing with. So rating companies, they have a certain kind of classification, and already the classification offers opportunity to reduce it. So basically, our problem was that the tails were underrepresented in our sample, and by using a different way of representing the ratings, so from the original 21 just reducing it to 9, we had more balanced classes, though of course the extremities were always a little bit underrepresented. But actually, in the end, we found that weighting didn't improve in any way the capabilities of our network. So this is just a very easy processing for your targets. And let's now go to the model. And I guess you are all very expert about neural networks. So I think we can pass very quickly from this slide to other topics. But one point is expressing this box here, is that we had to deal with a very high dimensional categorical feature, which was also very, very important. It's called NACE, NACE2, and it is a categorization of the sector where the companies operated. Now, the sector is actually very important because each sector has different competitive scenarios. So each sector has different companies operating in it, as different way the companies interact, and also has different problems, because you can have a company dealing with services, a company dealing with energy, a company dealing with consumer products, and you can imagine each company, given the different sector, have a different way of keeping their accounts, of deciding if to take financing, of deciding how to spend money. They have completely different characteristics. So basically, even if we have the same KPI, a KPI can be read in a certain way in a sector, and in another way in another sector. So it was very important to represent this information, but we couldn't use the one-hot encoding because it would have made really the network dealing with too sparse data. And when the data is too sparse, a neural network cannot work properly. It's very difficult to propagate, to back-propagate the error, to reach convergence, and also to find the right, the best solution in terms of weights. So you may be wondering how many codes you have. Actually, there are many codes in the NACE categorization, but basically we had almost 1,000 codes. So really, really too much. And this solution we adopted is something that maybe if you have played a little bit on Kaggle, have taken some tabular competition, is quite popular and renowned. It's called embeddings. And embeddings is the solution where you have this case of a single high categorical or multiple high categorical features that you have to represent in the best way. How does it work? So this is a very simple schema of working. Basically, you just feed your neural network with an encoding, label encoding in this case, of your high categorical feature. Let's imagine your feature has labels, textual one, like ID 8080, something like that. It could be anything, basically. With label encoding, you just transform all these labels into numbers. So you have 1,000 labels, you have all your data encoded with an ordinal number from to 1,000. And at this point, when these numbers, which are integers, enter the neural network, and we have to follow a specific path inside the neural network, they are automatically, in a very smart way, kind of one-hot encoded. And they are inside the neural networks, multiplied by a vector by matrix multiplication. And this matrix is a weight matrix that helps to recombine the information inside the one-hot encoding and just project it into a result of a certain dimension that you decide. So for instance, if you have 1,000 categories and doing one-hot encoding, you have 1,000 possible features, you may decide, which are sparse, you may decide just that's enough for you to have 4 features. And this procedure will just project all that information into 4 dense features. And dense means that they don't have zeros, they have some value. And this is the best for your neural network. Let's see again this from a very practical example. So in this case, you have a level 2, and here you don't have 1,000 levels, you are a little bit less, but the example should give you an idea. So basically, it's one-hot encoded. It means you are just doing multiplication with one single row of this matrix. And this matrix has initially random values, but by, training more and more your data by backpropagation, it will get the right values. And by the multiplication exactly on the row that is activated by that label, you have your projection. Of course, this embedding matrix its dimensions are given by the initial number of levels and by this m value, which is decided by you. It's kind of upper parameter. You have to test different solutions. But basically, you try from small numbers like 2, 4, 8, 16, and so on. And you make some experimentation and you find very quickly the right number to be used. And in our case, we wanted to be sure, since some categories were very little represented. So we have very few companies, because sometimes you cannot sample more, or because actually there are very few companies in certain sectors. There are some very huge companies, almost quasi-monopolistic ones, and we use special dropouts. So it means that differently from the dropout, which just randomly, blanks certain size your matrix, it just blanked, randomly certain columns of our matrix. In this way, the learn weights in the matrix were not really too much dependent on specific cases, and it was a way to regularize. And it is very important using embeddings. In my experience, especially in Kaggle competition, okay, there are many pre-made, tabular, like Tabnet, for instance, the most popular one, like Tabnet, neural network for tabular data. But the best is always just to write a very simple, and there are many frameworks. You just need to go to any competition. Just a very simple neural network and using categorical embeddings for your categorical features. And that's enough. And this is something that gradient boosting cannot do. Gradient boosting actually just can split, of course, on categories, but it doesn't have the same efficacy of neural networks in representing this kind of information. And especially, this is something that I want to remark, is not just that you have then a trained matrix that you can reuse with such embedding, such projection, especially if the NACE is using a lot of banking applications. So it's very easy to reuse, like Pinterest does for its pins. So basically they use it for the interest, and they have matrix that can transform certain categories into related scores for neural networks or Instacart. So it's products that are already embedded into a value to be used in neural networks, but you can reuse them also in gradient boosting itself, and they are really a great advantage. Another great advantage that probably it's better already to explicit before going on is that, as I mentioned before, in our problem especially, we had an idea of the features to be used, but we really didn't know the process exactly, what ingredients required, because writing companies, right, they keep the secret. they know exactly how they do their things. So we need basically to do automatic feature engineering. Artificial neural networks can do that basically for you. In gradient boosting, instead, you have to do your own feature engineering. So unless you know very well the problem we are dealing with, you have very explicit knowledge of the features you are going to use, how they relate, and a body of knowledge that helps you to combine correctly the features. mm, Using a neural network can save you a lot of time and a lot of efforts, because it will automatically create for you the feature engineering you need for the problem at hand, and it's just necessary to experiment a little bit with the number of nodes and layers you have to use. Okay, I just go back to the embeddings. Here you can see that basically projected the embeddings. Here we use a T-snap projection in a way that made sense, especially in terms of financial terms for us. So it was a very good proof that it works and give us confidence about our work. And here basically the network we used. So I mentioned that everything entered into an input layer, and we already embedded the information, in this case of the categories at this level. We did spatial dropout, and so we obtain the scores for each sector that we have to use. Then, using another input layer, we just inputted all the other quantitative features, the one encoded one, the numeric one, the KPIs, and we concatenated everything together. It's very easy, and then we just had a few dense layers, a dropout, in this case a Monte Carlo. We explain to you later what's that about, and then we just get the result, which is, in this case, a regression problem, because you have an ordinal sequence of classes. So from 0 to 8, we had 9 classes in this case, and so regression worked quite well. Of course, we experimented a little bit with the layers, so we use the Gelu and the Mish, which both gave good results. I also suggest you to consider the Selu, which is working very well, and you can find it in almost every recent Kaggle competition dealing with tabular data. It will give you a great advantage. And what are the results that we obtained? Well, they are quite good and comparable results with a lot of literature we found, but of course we were quite better than any other model we used. In particular, they become even better when we tried and we tested point using a different metric for our early stopping. I mean, we use the mean square error for our optimization, which is a classic metric. But basically, we noticed that it made some errors. Why? Because the mean square error penalizes, of course, the examples that are predicted very far from their true class, true value. But it tends to exchange the examples which actually are more weighty, let's say so, more particular, with the examples that are less weighty. So it tended to do strange errors, basically, and we didn't care that some error appeared in our prediction, but we did care that the error was not too far from the truth. So experiment with the quadratic weighted kappa gave us the confidence that when the network was wrong, actually it was not so wrong, not so far. And we use it not as a loss function, but as a metric for early stopping, and that worked very well. Now, maybe you are not accustomed to this metric. Actually, it has been using quite a lot of Kaggle competitions dealing with ordinal data. So I just remind the first Pathfinder competition, which was based on this one, and the score is actually based on statistical reasoning because uh, previously you had to evaluate when judges evaluate differently a certain measurement. So in statistics, especially psychology, a lot of measurement are done human based. So you have people, experts that tell you, okay, for me it's A, or for me it's B. And you usually collect multiple elements, evaluations from different judges. And then you want to know if their evaluation is basically similar or not. So if they have a convergent opinion on that case or not. And so you use the kappa statistic, which is a way to evaluate if a series of predictions are just similar because of chance or because they are really similar. And this is very useful when you project it to an ordinal problem in machine learning, because especially if you weight the errors more as far as they go, so in this case using the quadratic, so just exponentiated by 2 the larger errors, it can help you to figure out if your predictions are really very different from the predictions that you are trying, from the ground truth you're going to match, and it will just give you an error which is more ordinal in nature than the mean square error. And this worked really fantastic. And this is an idea that actually we took sincerely from Kaggle competitions, because it's something that we saw working so well for these competitions. And here are the results. Obviously, the deep neural network is going very well. It has a quadratic weighted kappa of about 0.864, which is fairly better than linear regression, logistic one, but also gradient boosting, which actually was about 0.8, 0.82, if I'm not remembering too badly. And this is due to the feature engineering automatic of a neural network and to the embeddings, which just boosted its results. And here with confusion metrics, as you can see, the quadratic weighted kappa really kept its promise, because if you have errors, usually the errors are just very near the true level. They are just one, we call it notch, one class less or one class more. It seldom went farther, and so it really worked very, very well. Of course, we explain everything by SHAP, which is something that I mentioned before, not typical of Kaggle competition, but I suggest you to consider sometimes using SHAP in your Kaggle competitions, especially in order to figure out why your solution makes certain errors. It's kind of, error analysis. In our case, it was different. We had to explain why we made some decisions, but having an explanation of the decision of a network or any other algorithm you are using is also very important for you to figure out if you are doing something wrong with your examples, or if you could do more in terms of feature selection or cases selection and so on. And I also spend a little few minutes, just 5-10 more, and then I'm open to your questions about the improvements, because we keep on working on this shadow rating, and we had more ideas how to improve, and especially how to make neural network more competitive against our more traditional methods, especially in this problem. So I mentioned to you before that we had very little observation. So basically, we had many nodes. I cannot tell you how many, but you can imagine we had more nodes than examples. And this is typical when you're just working with tabular data. Even if word is filled with tabular data, even tabular data often for a problem you need is not enough. And your networks sometimes can get very complex. You have multiple layers, a lot of nodes, skip layers, and basically, they are just over parameterized against your examples. But we found that it worked. it worked very well, and we wonder why. And basically, we had kind of answer just 1 year ago about when we started to talking around about deep double descent. And deep double descent actually is happening not in tabular data. It's more common when you're dealing with images, when you're working with transformers, and so on. And just stated very simply, many researchers found out that they just set their networks, for example, they start training, and normally we saw, especially at validation, so the validation curve, that the network just started performing very well, and after a certain stage, it got worse. And okay, the imaging is sign on overfitting. The network is overfitting, so probably we have to stop. But for some chance, some researchers just let the network go, and after worsening its performances, after a while, the network just got working very well, and even it improved and become kind of state of the art results in its field, in its task. And I remember many tweets about, oh, I forgot my neural network training for all the winter vacations, and when I come back, it had a total results, and I'm writing a paper on it. But you may wonder, why does this happen? How is it related to the problem that you have so few examples and you want to create very big complex networks to solve it? Basically, it's the problem of the regularization and the complexity of your model. Neural networks are commonly known as very complex models. So in terms of bias and variance, we have an high variance because they have a very strong capability of representing your problem with a universal or more universal coverage of possible function. Deep neural networks are called universal approximator. They can, if you give them enough layers and enough nodes, they can approximate any function you can come with. So let's imagine that our problem is the problem with sinoid problem that you see in this representation. Of course, if you are using a polynomial approach and you just giving a few degrees when the degree is necessary to represent it, you are underfitting your problem. So you are giving too much bias when you actually could use a model with more variance. When, of course, you just match the degrees perfect, you should get a very good prediction. And it's a common example in all courses. They show you, okay, let's use a higher degree of polynomial, and you see it's so wiggly, it's very strange. It will give you very absurd results when actually you are just testing it through. But very problem is that if you exaggerate even more with the degrees, and in this case you use a very, very high degree of representation polynomial, basically the results will be much better than in the case of the underfitting, or in the case, of course, of a high degree but very wiggly. Why? Because basically when you are using a high degree of freedom, yes, you are overfitting your problem, but in doing so, you are basically probably more fitting better the separation boundary that your neural network should find in solving your problem, because it's a matter of a function, right? So if you give more freedom, more nodes, more parameters to fit, it will probably find an hyperplane which is better for your problem than just giving a very rough hyperplane, or an hyperplane complex but not enough complex. So the strategy appears clear, and it's very important to have this present when you have work problem with tabular data and neural network. You have to create another representative network. So network with many layers, you have to start very complex. And this is something that we found out illuminating, because myself a few years ago I gave a country example of proceeding. I said start small, start with a few layers, start maybe with just one layer, you start with a few nodes, and then you grow complex. No, it's better to start very complex and then put some regularization. For instance, you can use dropout, and we use dropout, and this helps a lot. You have an overstated network, and by using dropout, you are masking periodically by a random choice part of the elements in your matrix multiplication uh, inside the network, and that can reduce its capacity, still keeping all the freedom to represent, if necessary, very complex functions, and it works very well. In our case, we used it's very simple to be implemented in Keras, a particular type of dropout, which is the Monte Carlo. What is the difference? Basically, when you use dropout, your network uses a train time, test time. You have a system to rebalance, the fact that you have masked some of your elements of matrix multiplication in the training, and then is actually not operating. It just a resizing of the outputs of your layer, and it doesn't work. With Monte Carlo dropout works even at prediction time. So you have random masking of your matrix multiplication even when you predict. This causes the fact that if you predict multiple times for the same example, you don't have the same results. You have a distribution of results, which is fundamental in order to provide uncertainty to your estimations, and also be able to give confidence boundaries for the people using them. So you just don't say it's, for example, this rating, but you say it's this rating with probability of 95% of being between this rate and this rate. This is more important and more useful for our kind of users. So this is a trick that you can use not for Kaggle competition, though I had occasion to use it, especially when I couldn't retrain many models, and having a dropout can help you to make multiple prediction with the same network on the same case, and then you can just ensemble all the predictions. And this actually brought a lot of improvements, but the greatest improvements, that is another very important aspect that gives an edge against gradient boosts into neural networks. We got it using augmentation technique. And here you may be shocked, because augmentation is something that you are used to know. It's applied to sometimes text, but most often to images, but it can be applied also to tabular data. And in particular, we use a mix-up idea. I just very quickly explain to you. In images, you just imagine you can just treat the image as it is, or you can cut portions, it's cut out. You can cut and mix portions of different images. And mix up, it takes an image and it just fuse it with another image. So in this case, if your image is a dog, if you mix up, it picks another random picture, in this case is a cat, and you can see some, like a ghost, some shapes of a cat, together with a dog. And in our problem for tabular data, it means that every time we pick an example, we can just test if we use the example as it is, or if we want to mix it up. And we found that using 85% probability of keeping the same original data worked very well for our problem. But for the other 50% of situations, we just mixed with some case which were similar, not too far. And we just use the target, of course, for this, calculating this similarity. And then we picked randomly some features from the new example, and we just put these features into our original one, creating a new example. So our neural network, even if it had a limited number, I mentioned before, 2,500 cases, it could augment the number of examples. And we noticed it. It was not just that we kept on presenting new examples, who, of course, very similar to each other, because only a small portion was changed. It was the fact that we were giving the network the opportunity to learn the boundaries in separating the different classes better. So we help the network to fill the gaps because with just 2,500 examples, the network had a lot of possible combinations of feature values unknown. We didn't know how to deal with it. So he had a solution, separation solution, which was mathematical, but not too well grounded by providing, and I just showed you what I mean for boundaries. So if you apply any kind of algorithm, in this case a bidimensional example, you can find the separation between classes or between values, and for each algorithm it's very different. In the case of neural networks, is an hyperplane and a nonlinear one. And it helps to have a smoother hyperplane separation one and to be more able to understand new example, to be more general. So just to sum up, here we have references to all our work. You can find our shadow rating paper, the Monte Carlo dropout, and the mix-up data augmentation. I want to remind you that, okay, if you have a problem, tabular data is okay to take gradient boosting, running it, maybe is the best things to be done. But in certain cases, neural network can work better and can even, overperform these classic solutions by XGBoost or LightGBM. And why? They work very well if you have cases where you have to do feature engineering, but you don't know how to do. So basically, you need some automatic feature engineering. If you have high categorical variables, because embedding layers are the secret to make any problem with tabular data to work fine with deep learning, and also augmentation. Augmentation can, if done smartly, can help you even with tabular data and is a great edge against our traditional methodologies like gradient boosting, which really don't have this opportunity. So I just close my presentation here. I thank you a lot for your attention, and I hope it has been illuminating for you, and I'm open to any question or curiosity.
Sure. Thank you, Luca, for like complete overview of the thing, because I myself have a little bit of experience in this domain, but your explanation around shadow rating and all those things was really interesting, and I also took notes out of it. So thanks for the
Thank you.
session. Yeah.
You're welcome.
And
You're welcome.
one thing, it's like one of the community member had asked that while we are working with such a highly regulated industry, right? When we are trying to work in banking, finance, and all those insurance kind of industries, getting like those regulations and all those factors, data security, ethics, and while we are trying to move towards ethical AI and all those things, have been in lot of news when we are trying to utilize data and machine learning kind of approaches to
Yes.
these domains, right? So where
Yes.
do you see these kind of like algorithms or all those things being used in future, provided that we have more and more data security and privacy concerns coming in?
Okay. I have to say that we have an advantage. We work with companies, right?
Hmm. Hmm.
And companies, they are not so protective in terms of privacy. But
Hmm.
in my opinion, I think that when liberty, freedom, security of people are at stake, you really need to make very explainable models. So even if you can get an edge with very complex approaches like deep neural networks, it's paramount to explain why they provide that answer. And sometimes even a sharp explanation is not enough because it's an
Hmm.
approximation after all. So I think that we will keep on doing easy modeling and theory-based, theory-driven, in order to preserve important values in our society. After all, myself, I cannot tell why a model decides a certain thing, because especially complex models can pick particular feature information that you really can imagine why. So
Yeah.
In my experience, and is also our rule, uh, un, unless you are forbidden to, of course, you can use these tools. And in case of
Mhm.
companies, you have plenty of freedom. But when it touches individual, liberties, freedom, interests, is very important to always provide an explanation. By the way, in Europe, we have GDPR, which is a very, very strict regulation, and we do have to explain why a model says a certain thing, given a certain input.
Exactly. So I got your point. Like we would, our main goal moving ahead would be trying to decipher those black box thinking that we have for a machine learning, right? Whenever those regulations hear about data science, machine learning, they all about one of the first impression that they have, this is a black box, or like we might not be able to explain all those things. So thanks for the answer. And one of the community member asks that how to handle large amount of tabular data, like 1 million data, or like example, this is an example that
Mhm.
this community member is trying to ask about how to handle the large amount of tabular data.
Okay, in this case, of course, we didn't have these problems, so I didn't mention it explicitly. But neural networks are the best way to deal with it because
Mm,
you can write a, you know, data set class feeding like a generator your neural network. So even if you have millions and millions of examples, you can handle by batches enough large for your network to learn that you can fit automatically just picking them up, for example, from your data lake or your repository. So it's quite suitable for this large number of information. But sometimes, in my experience, maybe you don't need to. Sampling is a very known technique, and so you can reduce the number of your examples to a few significant ones. Of course, you need to understand the data you are going to sample because sometimes you can get profitable results from very niche sets of examples. So you have, for instance, to understand that you have to represent very well certain, a mix of features or characteristics in respect of others. So just the simple sampling, the random one, maybe it won't suffice. You need to create something stratified and controlled. But I always suggest before feeding millions and millions of raw into that set to be fed into a neural network or another algorithm, to reflect if you do need them or not.
exactly. That's a golden piece of advice before moving ahead. Like it helps us to get the real crux of the things that we have, right? And to focus on the things that we majorly want. So that's a very
Yes.
good advice.
Yes,
And
and
like
if you really
another.
need to, a neural network can be a splendid way because since you are giving batches, if you
Mhm.
just regularize them, if you are providing a lot of noise, and it happens because you cannot see exactly what's inside 1 million examples, right? A lot of noise and problems will just slip under your eyes. The neural network can really clean them for you, which is
Yeah.
won't be happening with other algorithms.
Yes, yes, truly agreed. So another question is how to approach the missing data in kind of 1 million or in financial data.
Okay, so if you are missing the data and you have a very large number of examples, you can write an imputation model, or if you are just, you have to provide very fast your results, a very simple trick, and which is used also in GLMs, is to standardize your variables. So you center them in the mean. So basically, every missing will be zero, right? And so
Yeah.
your neural network, you just feed the numbers, and missing zero, it will deal with it. But you also write a feature pointing out the missing indicator. So telling you what cases are missing that value. So it will use, provided your features standardized, when it sees zero, it will use bias for imputation, but the bias will be corrected by your missing indicator. So if you have some, for example, interaction with other variables, so you are not having missing at random missingness, it will catch and intercept also all the information from other variables. So standardize, use zero as missing value, but also provide missing indicators, and
Indicators.
it should work quite fine.
Yeah, yeah, makes sense. And it really works. Like in certain cases, it definitely works. So yes, thanks for sharing your experience. So as we are our one time, we would try to get more of your idea on the recent book of yours, right? The Kaggle book.
Thank you.
So yeah, so like we have got a lot of love from the community members that the book has been really good and it's really useful. So we just wanted to convey the thanks from their side to you on this live event. So like
Okay,
for yeah, and like if we were to summarize your journey of writing books and the latest book of this, the Kaggle book, how has been your journey into writing books around data science, machine learning, and because you have written multiple books over the time, how has the times changed? How has the perception of public towards data science, machine learning changed? And how has your way of writing books in
wow.
these domains changed?
That would take another hour, I think, to explain. But I can tell a few things very important. First of all, if I write, it's because of Kaggle.
Mm-hmm.
If it weren't for Kaggle, I would have become a technical writer. It's just because I was participating in many competitions, and suddenly I found, classified ads in Kaggle looking for an expert to write a book. And it was a little bit, how can I say, it's shameful. Say, oh, why should I answer? There are a lot of very excellent Kagglers who could answer that, but I did, and everything started from there. So I own Kaggle, the opportunity. And when I started, there were very few books around. So I wrote very basic books, and I had a lot of opportunity to write about very diverse topics. I wrote a lot of dummies books, but also very practical ones with publishing about how to have, for example, essential manual for data science on your table that you can open and just use it. In the recent years, the scenery has become more complex. There are more books. Sometimes I regret writing so much because it also means I have less time to read. And there are so many cool books around. I really would like to read them all. There are many, many books. So I personally tend now to choose very well if I have to write a book about the topic. As far as the Kaggle book, I have been in Kaggle for over 10 years, and it is something that I've been thinking about a lot. What I can do for Kaggle, how can I give back all the fantastic opportunities that Kaggle gave me? And I noticed one thing, and it was very important for all the beginners, all the people using Kaggle on a regular basis, but we are not the kind of grandmaster that are always, exploiting all the opportunities of Kaggle. We're just trying something here and there. Every time you start a competition, you have to start from scratch. You don't have the information. You have to rely on the people discussion, and there are many, they are very kind to provide you the basic informations. So you want, for example, you have a large data set, you want to squeeze it a little bit because maybe the data types are the wrong one, they are just floats and you can use integer and so on. Whereas the code on Kaggle is free to everyone, but if you don't know where to look for it, you won't use it, right?
Yeah.
There are many other tricks. So certain error metrics, certain ways of, hacking your neural network. There are a lot of information on Kaggle, but if you don't look properly for it, you won't find it. So the idea was, let's write a book which has all the basics you need to know to take on any competition you want. Then, of course, you always have to rely on discussions because discussion will provide, very on the problem information, and very fantastic for helping you to achieve higher ranking in your competition. But as far as the basics, we wanted to provide a book that everyone can access and immediately leverage for the enjoying the best Kaggle. Because remember, Kaggle is really fun, is uh, incredibly fantastic, to addictive, to work with so many problems, but is also very important for your career, because it will expose you to problems that maybe you are not facing at work. It will help you to test your skills on a lot of different problems that can help you grow as a data scientist. So uh, look it as a competition, but also as a great playground for learning and improve yourself.
Yeah, like I truly agree to you what the pointers you mentioned, and thanks for giving us a brief about how the journey started and what was the motivation behind writing this book. So thanks for that, and thanks for your
Pleasure.
time today, for joining us on our third anniversary meetup. And it's really a pleasure to host you. And we really
Thank
hope
you.
and we really wish all the best to you for your career. And thanks again from the community for writing the book and for sharing the knowledge today.
Thank you to
Thank
everybody. It
you.
was fantastic being here today. Thank you.
Thank you. Stay safe. Bye bye.
Bye bye.